All right, hey functions class. The bell rang because of the pep rally this morning before we got a chance to finish our extremely important lesson on completing the square. So I want to talk about this right now. So basically, take out your notes from today's class and just like do these problems really quick as I do them. There was a problem x squared plus 7x plus 5 that I wanted you to solve, so just do that. I'm well aware that you have all completed the square before, or at least I think you do this in Algebra 1 and definitely in Algebra 2, but nonetheless, just do it. And yeah, so pause or whatever, get ahead of me, or maybe you're already done if you're very fast. How do I do this? Well, basically I do a little bit of that, get the 5 over to the other side where it cannot hurt us, and then I have to figure out what is the important number which goes here to make this a perfect square trinomial. So this is just going to be like 49/4, I guess. So if I add 49/4 to the left-hand side, I have to add 49/4 to the right-hand side also. And this is now a perfect square trinomial, x plus 7/2 squared. Oh, when I'm by myself, I probably just am gonna like mess up. So when I do something terribly embarrassing and solve a problem wrong, you can just laugh for hours. It'll be great. So is that right? I think it is. And over here, I then get 49/4 minus 20/4 is 29/4. Now, if something squared is 29/4, then that something must be plus or minus root 29/4, or plus or minus root 29 over 2. And so finally, x is -7 plus or minus root 29 over 2. Looks good, I hope. Yeah. Yep. Okay, now, when it gets really hard for Algebra 1 students all across America is when we are solving problems like this where there is a leading coefficient. So you have basically two options. Option number 1 is to factor out the leading coefficient, and option number 2 is to just divide. So let's talk about, let's do option number 1 first. I take this problem and I factor out the 5, so I get something like this, and move the 9 over to the other side of the equation where it cannot hurt us. I factor out the 5 here. What number goes in the blank space? Well, this is going to be 9/4. Yep. But the key step is in realizing that at the moment with my purple marker that I write 9/4, what I have actually done to the left-hand side of this equation is I added 45/4. And so I must add 45/4 to the right-hand side also. So, okay, not hard once you've done it before. So then this becomes 5 times x minus 3/2. And over here, I get -36/4 plus 45/4. So that is just 9/4. Cool. And thus, I get x minus 3/2 squared equals 9/20. And now I basically have this back like a problem that I already know how to solve. I can take the square root of both sides, or rather, if something squared is 9/20, then that something must be plus or minus root 9/20, which I can write as plus or minus 3 over, and root 20 is just 2 root 5. We can rationalize this by multiplying by root 5 over root 5, because for mysterious reasons we don't like square roots in the denominator, so I get 3 root 5 over 10. Yeah. So my final answer is that x is 3 halves plus or minus 3 root 5 over 10. And this is a perfectly fine way of writing the answer to this problem. Option 2 says that we could instead take that original problem and we could just divide both sides by 5. So if I do that, I'm going to get x squared minus 3x, and then I'll just move that over, equals negative 9/5. This is almost the same thing, it just means I don't have to factor. It means I just have a problem which is just like my original problem. So what do? Well, I add 9/4 again. So I add 9/4 to the left, so I add 9/4 to the right. And this is x minus 3 halves squared, and this is going to be 45 minus 36 is going to be 9/20. And now I'm exactly where I started over there. Okay, cool. What else? This is completing the square. Let's do another one. Let's like do another problem. 28x minus 49x squared equals 1. Okay, so just like do that problem right now. Yeah. And I will do it also. Yep. So I guess I want to do it like this. Um, 28 over 49 is 4 sevenths. Looking good. So this is 49. I will add whatever that is, 4 49ths. But at the moment that I write 4 49ths there, I really have just added 4 to the left-hand side of the equation. So I add 4 to the right-hand side of the equation also. So, and I got this back at 3 49ths. And this would be root 3 over 7. So x is 2 plus or minus root 3 over 7. Okay, awesome. Well, it seems as if I'm kind of doing the same thing over and over again every single time. It's very much like a pattern. It's algorithmic. It's formulaic, you might say. I have a quadratic, I factor out the leading coefficient, or I divide by it, and then kind of like take this middle number, take half of it, square it, add it to both sides, wouldn't it be great if I didn't have to complete the square over and over again every single time, but instead, since it's just a pattern, perhaps I could take this pattern and just like, turn it into almost like an algorithm. So let's do it. If you've never seen this before, it means you had a terrible middle school education. But I bet there are about 3 of you in this class who have actually never seen this before. So for those of you who are going to do it right now, it's a classic part of your education. We are going to solve a quadratic formula once and for all via this method, which seems to solve all quadratic equations, which is completing the square. Okay, so we take this, and I'm going to solve this. I'm going to do it. I'm going to do the divide by a way, although it actually really doesn't matter. But I'll just divide by a. So if I divide by a, I get x squared plus b over ax equals negative c over a. Okay, looking good. Now what I need to do is I need to add something here which will complete the square. So that number I need to add is take half of that, which is b over 2a, and square it. That is going to then be a perfect square trinomial. So if I just added that to the left-hand side, then I need to add that to the right-hand side also. So this is b squared over 4a squared. Okay, looking good. Over here I get x plus b over 2a, squared. And over here I'm going to get, well, I should get a common denominator now. I should multiply by 4a over 4a. And I get b squared minus 4ac over 4a squared. Wait, what? Oh my god, it's amazing. I've seen this somewhere before. Alright, continuing on, I get x plus b over 2a. This must be then plus or minus the square root of all this stuff. B squared minus 4ac all over 4a squared. And in fact, what I have is just negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. This is the quadratic formula. The quadratic formula, which is so great and awesome, is simply what you get when you apply the completing the square algorithm to a generic quadratic equation. It essentially does the entire completing the square for you in just one step of memorized sort of formula. So anytime you don't feel like completing the square, you can just use the quadratic formula instead, basically. Okay, pretty much like one more thing to do. Let's flip back over here, and it's going to do this weird focus in, focus out thing. I can also, this completing the square thing is also useful for graphing purposes. Suppose I want to graph a quadratic equation, 3x squared plus 30x plus 52. Okay, this is kind of hard to graph and sort of annoying and weird, and we, at least in functions, have not graphed anything like this before. So, how can we do it? Well, if only you're in one of those nice forms that I know how to graph. And essentially, I can use the techniques of completing the square to accomplish this for me. What I'm going to do is I factor out the 3, x squared plus 10x, and move the 52 over to the side where it's not bothering me. And then I can figure out what goes here. Well, it's pretty clear what goes here. The number 25 goes here. And what I have just done is to add 75 to my function. And if I add 75 to my function, then I need to subtract 75 back out again so that I have not changed the function at all. And then like suddenly, just magic happens. This is x plus 5 squared, and then that's just like minus 23. Out of nowhere, I have now rewritten this function in a form which makes it really, really easy to graph. Because I know what y equals x squared looks like. It's one of my parent functions. So this is simply that function which has been stretched out by a factor of 3, moved 5 to the left, and moved down 23. So for someone who is a master of transformations, I now can take any quadratic and I can put it in a form in which graphing it is very, very simple. So I have this parabola, and picture not to scale. I'm going to go 5 to the left and down 23, and I know that the vertex of the parabola will be there. Cool. So this parabola has a vertex at -5, -23, and for that reason, this is sometimes called vertex form. The vertex form of a parabola is a form in which it is very obvious to tell what the vertex is. And using this completing the square, I can basically put any quadratic in vertex form, and thus I can graph it. All right, one more quick thing. Why do we call it completing the square? There's kind of a name for this. Well, I don't know. If I take some expression like x squared plus 6x plus 4 or something like that. And to complete the square, you know, I want to like add 5 to this or something. So how do I do this, or why is it called complete square? Because it's based on a way of sort of thinking about products as areas, and if you had like a really good Algebra 1 teacher who taught you with like algebra tiles, then you've seen this before. So take, basically, it's supposed to be a square. Here we go. Let's do this. So what we have here is like a square of side length x and x. And then I have like 6 of these x's. So I think of them as 6 of these little strips, each one of which is like 1 wide and 6 long, or rather x long. But I have 6 of them. Those are supposed to be 6 congruent strips, each one 1 by x. And then I also have like 4, so that's just like, you know, 4 little squares that are all 1 by 1. Well, what I can do is I can form a square diagram out of this. So I have my square of side length x, and then I just put like 3 of those guys here. And then I put 3 more here. Yeah. And then I put these little 4 guys here. And what I have kind of forming here is like a square. So what I would normally add to this to complete the square is 5. And we see that if we complete the square, which is, of course, this is x plus 3, and this is also x plus 3. So we're completing the square is a kind of is a geometric reference, or it's a reference to the geometric representation of what we're doing. Okay, one more thing that kind of goes along. I usually do these lessons on the same day. I'm going really slow. Feel free to watch this video on like 1.5 speed or even higher. But you should definitely do the problems yourself anyway. Don't just watch. Watching is stupid. Let's solve some equations. Let's solve some absolute value equations. Okay, so we know that the definition of absolute value is the absolute value of something while it's positive, if that thing in the inside is positive or 0, and it's the opposite of that number if that thing is negative. So suppose we want to solve an absolute value equation like absolute value of x squared minus 6 equals x. This is like an equation that I might want to solve. So, yeah, how do I solve this equation? Oh, the stupid focus thing, I hate it. Let's see, do I get the whole board there? Mm-hmm, I do. Okay, well, I basically have to consider the various cases. I have to consider the case that the thing on this is the good way to do these problems. I have to consider the idea that this thing on the inside might be positive and the thing on the inside might be negative. So this is really like a case argument is required. Serious people, when confronted with an absolute value, simply just get rid of it. So when is the absolute value of x squared minus 6 going to equal to x? Well, the case one is that x squared minus 6 is positive, or 0. And case 2 is that x squared minus 6 is less than 0. Well, if x squared minus 6 is greater than or equal to 0, then simply this means x squared minus 6 equals x. So I have sort of defined away the absolute value by treating it in a case-like way. Now I have a simple quadratic which I can solve. So x squared minus x minus 6 equals 0. And here I have a factoring situation. So that's x plus 2 plus 3. I think I did that correctly. So I get that x is negative 2 and 3. On the other hand, if x squared is less than 6, then the meaning of that symbol is negative x squared, or the opposite of the inside. That's simply what the absolute value of something is if the something is negative. It is the opposite of that thing. So I get negative x squared plus, is this making sense? I think this is making sense. Negative x squared plus 6 equals x. So then I get x squared plus x minus 6 equals 0. And that factors a little bit differently. x plus 3, x minus 2 equals 0, and thus x is negative 3 or 2. Alright, now, the lazy man at this point just says, okay, those are my 4 solutions to this problem. Not so fast. Some teachers will simply caution you to, anytime absolute values are involved, to just like raise red flags, and, you know, flag, it's red, I promise. Adjust your settings on your computer, and basically to test these one at a time to see if they actually satisfy the equation. For example, I can plug in negative 2. If I plug in negative 2, well, it's pretty obvious this is not going to work, right? If I plug in negative 2, I get 4 minus 6 is negative 2, but the absolute value of negative 2 is 2. So this is going to say 2 equals negative 2. So that just doesn't work. So negative 2, extraneous solution or whatever. Does 3 work? Yes, because 9 minus 6 is 3. Absolute value of 3 is 3 equals 3. So 3 works. Negative 3, does negative 3 work? Well, again, clearly no, right? If I plug in negative 3, I get 9 minus 6 is 3, I get 3 equals negative 3, so that doesn't work. Does 2 work? Yes, because 4 minus 6, negative 2, absolute value of negative 2 is 2. So I have the 2 solutions, 2 and 3, and I excluded the other 2 by simply testing them and seeing if they didn't work. That is one way to do it. That's how some teachers teach it. Just split it up into cases and then just do all the problems. If you want to be a little bit more careful about understanding why these extraneous solutions arise, you can simply observe that negative 2 cannot be a solution because it does not satisfy the case even, right? Because if x is negative 2, then it's not true that 4 minus 6 is greater than or equals 0. So if you don't actually have to test the numbers back in the original if you're simply careful with making sense of whether this number is even possible in this case, and the answer is it isn't. And same thing over here, right? Negative 3 doesn't satisfy the definition of the x's which we're considering on this half of the problem. My goal is to talk fast enough that you actually can't understand me on 1.5 or 2 times speed. All right, let's do 2 more absolute value problems. Here is one that is kind of weird. Absolute value 3x plus 1 equals absolute value 5x minus 2. Oh no, we now have multiple absolute values in this problem. That is pretty annoying. What are we going to do about that? Answer, we just have to treat them all separately, you know, like with cases and stuff, technically speaking. So, let's do that. Well, basically the 4 cases are that they're both positive, that the left one is positive and the right one is negative, that the left one is negative and the right one's positive, and finally that they're both negative. Well, if they're both positive, the insides I'm saying, then this is just the equation 3x plus 1 equals 5x minus 2. Because when I say positive, I mean that 3x plus 1 is greater than or equal to 0, and that 5x minus 2 is greater than or equal to 0. Anyway, what happens, I get 3 equals 2x, so I get x equals 3 halves. I think I did that right. What if one is positive and one is, this is positive but this is negative, the insides? Well then, this just means 3x plus 1, but the 5x minus 2, if it's negative, means negative 5x minus 2. And so this is just 3x plus 1 equals negative 5x plus 2. You should be doing these problems along with me. So I get 8x equals 1, so I get x equals 1/8. I think I did that right. What if the left one is positive and the right one's negative? Well, then I'm going to get negative, then the left one means this. Okay, but this ends up being just the same thing. I've already solved this. And if they're both negative, then that means that the left means this and the right means this. Well, algebraically, I've also solved this already. This is just a repeat algebraically of case 1. This is just a repeat algebraically of case 2. Okay, are these both actually solutions? Let's just plug them in and test them. Does x equals 3 halves work? Well, it says, let's see, 9 fourths and 1/4. It says that 13 fourths equals, 13 fourths, no, 13, try that again. 9 halves and 2 halves is 15 halves. And on the right, if I plug in 3 halves, I get, what the hell is going on? 15 halves. No, this is not 15 halves. How am I talking about? This is 9 halves and 2 halves is 11 halves. So pretty sure that this solution works just fine. How about x equals 1/8? X equals 1/8. So now I get 3/8 and 8, so I get 11/8 on the left. Yep. And on the right, I get 5/8 minus 4/8 is 5/8 minus, no, basically this is just not going to work, right? Wait, hold on. Let me try that again. I get 5/8 minus 16/8 is negative 11/8, which is, oh yeah, so I do get 11/8, so this works also. So x equals 1/8 also works. Okay, cool. This is solving absolute value. I got one more kind of cool problem. Oh, I should probably have left that on there for a while. Well, you can go back and check. Last problem, man, this is taking forever. Last problem, check this crap out. Absolute value x minus 3 plus absolute value x minus 5 equals 2. This is a very interesting problem, which I actually put on a test in my first year teaching, and hilarious things resulted. So now I have, again, I'm going to have to split this up into cases and this up into cases. Now I'm not going to be able to exploit the symmetry of the situation to exclude certain of them. So I'm actually going to have legitimately 4 cases. So let's consider the positive case, and by that I mean the x minus 3 is positive and x minus 5 is also positive. Let's consider the positive negative case. We'll consider the negative positive case, and we'll consider the negative case. Okay. The positive case says that that's positive and that's positive. So I get that x minus 3 plus x minus 5 equals 2. So I get 2x minus 8 equals 2. 2x is 10. X equals 5. Things looking good so far. And if I plug in 5, I get 2 plus 0 is 2. So in fact, this is a solution. Everything's good. Alright, if this guy is positive, then he just means x minus 3. If this guy is negative, then we just mean the opposite of x minus 5. So I get x minus 3 minus x plus 5 equals 2. Suddenly, I get the equation 2 equals 2. What the hell is going on here? What is going on, class? Well, all real numbers? When I first put this on my pre-calc A test, I got people saying that the answer was all real numbers. Well, not so fast, because what is the point? Well, maybe we'll do the rest of them. What about a negative plus? Now I get, if x minus 3 is negative, then x minus 3 must mean the opposite of x minus 3, plus x minus 5 equals 2. So I get negative x plus 3 plus x minus 5 equals 2. So I get negative 2 equals 2. Yikes! There are no real numbers! So maybe the solution is that there are no real numbers which satisfy this equation. Yikes! Even though I already know that 5 does. What if they're both negative? If they're both negative, then this means opposite x minus 3, and this is plus negative x minus 5 equals 2. So I get negative x plus 3 minus x plus 5, and that's negative 2x plus 8 equals 2, so negative 2x equals negative 6, so x is 3. Does 3 work? 0 plus 2 equals 2, so 3 also works. So what the hell is going on here? Well, when you consider the cases a little bit more carefully, then you sort of figure out what is actually happening. If this is positive and this is negative, what we're really saying is we're considering the x's in which x minus 3 is greater than or equal to 0, and x minus 5 is greater than or equal to No, and x minus 5 is less than 0. That's what I meant by considering the positive and negative case. Well, what x's satisfy that? X is greater than or equal to 0. X has to be greater than or equal to 3, and x has to be less than 5. That is just impossible. This case is nonsense. Let me make sure I'm doing this right. I'm in the positive negative case. Yeah. In order for us to be considering the positive negative case, I have to be considering x's in which x minus 3 is positive, but x minus 5 is negative, and that's simply impossible. There just are no such numbers. Wait a second. No, what the hell am I talking about? Yeah, I can be greater than or equal to 3 and less than 5. There are tons of numbers satisfying that. Specifically, all the numbers between 3 and 5. So the answer is, the reason why I get 2 equals 2, which indicates that any x satisfies this equation. It's true that any x satisfies this equation, but this case refers to x's between 3 and 5. And therefore, the actual answer is all numbers on the interval 3, 5 will be solutions, which is a very strange thing, but that's what the logic of this problem is telling me. Over here, I'm considering when that's negative, so that would be when x minus 3 is negative, and it's true that x minus 5 is positive. But this says that x is less than 3 and x is greater than or equal to 5. But that's a big time no, 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 no. I cannot be less than 3 and also greater than or equal to 5. So I got no solutions here, which is another way of saying no x satisfies this equation, but also this entire interval, this entire case is just like not really a case at all, because it's impossible for it to happen. And then over here, blah, blah, blah. Okay, so the actual solution to this problem is actually just all the numbers from 3 to 5. That is the solution to this problem. That is a weird situation which could possibly be made a little bit more clear by graphing. So anyone should be able to, and I had like one really smart kid who solved this problem completely correctly using logic and everything, and also made a graph of the function fx equals absolute value x minus 3 plus x minus 5. So we can do this now. Let's do it. I'll make a graph of this. You should do this at home. Absolute value x minus 3. What does it look like? It looks like that, pretty much. Yikes. And then what does absolute value x minus 5 look like? Well, now I go over 5